good programming practices with MIPS programming, since I understand a lot of people are probably entering concepts. This is preempting a lot of questions that people will have on how to design MIPS programs. So first off, I am Brad. I started the Reverse Engineering Interest Group. I used to be a tech lead for RC3, which is one of the clubs that merged into RITSEC. I actually enjoy assembly, so that's why I'm giving a talk on this, to try and share the stuff that I see and do to make my life easier, so that way you can make your life easier and have more time to do other things in your life, which is always a good thing. So let's preface this with assembly is really hard. I'm not going to sugarcoat that. Like, there's very little abstraction to various facets of the computer. You have to do manual memory management. You don't get if statements. You don't get neat things like objects and functions. You have to make all that for yourself, all from scratch. It's like someone hands you the cake ingredients instead of the cake. It's also very verbose, so you have to do like everything there's multiple lines of code for every single line of abstract rationale behind it. And so the difficult part of programming assembly well is actually coming up with a for the assembly you're writing. Anyone can vomit a code of frickin' spaghetti into a text file, but it's a bit harder to write it's actually about as easy to write a decently structured program in assembly, and it'll help you out a lot more than just going straight at it and hammering it out and making it look like crap. So first off, let's start with a list of things you might be doing wrong, or you might try to do wrong at some point. So for reference, I've never really been a TA for this class, but I've had a number of people come to me with help, and almost every single time there will be a new thing I read in their text files that make my eyes bleed. So I'm going to preface this with like some of the things I've seen that will make your life suck and will make it very hard for anyone to try helping you. Well, first off, if you just start writing assembly, you're probably screwed already, because you're not taking the time to think about the problem as a whole, and you're just going to run into all kinds of little implementation details. If you don't make functions, you're going to have a spaghetti code base. If you use registers for multiple purposes, then you're going to have to figure out what S1 means here and here and here and here, and oh, 3 lines, it's this thing, and then you're quickly hate your life when that becomes 6 registers that you've got multiple purposes for. If you have random jumps, you're going to have a bad time, because then you've got this really weird control flow. You want to have a well-defined control flow in your program. If you don't use the stack, then you're going to have a bad time, because you don't have any persistent storage. You're basically just making a functional program point. Stack is there for you, and it makes your life easier for assembly. If you're doing something clever, you're really going to have a bad time. I've seen people I'm like, what the hell is this? And they're like, oh, if I AND it with this bit sequence and then OR it with this bit sequence and then shift it left, it does this. And I'm like, what the hell? No, so that it might work, but make sure it actually like does the problem as a whole before you start making optimizations. One of the worst things you can do is premature optimization. It's how you have a completely unmaintained base. Optimize once you have everything working and in a workable state. You'll save yourself a lot of hours of sleep and panic. And if you don't write good comments, you're really screwed, because like if you write it and then come back 2 days later, you're going to say, what in the world is S1 doing here, and what is this logic here? Write a lot of comments. You will really appreciate it. Some more bad things. This is not a valid methodology for programming as much as a lot of you might think it is. Smacking your head into the desk repeatedly has a very limited subset of usefulness when it comes to solving problems. But it's chaotic. It doesn't reproduce problems it doesn't have reproducible steps. You're going to take longer to get there, and not only are you going to take longer, you're going to have a buggier product, which is going to take you longer to debug. What I'm trying to say is I'm trying to save you a lot of time by teaching how to do things at least moderately right. You have no obligation to obey any of these, but the stuff I'm going to present on is the most common things I see people doing wrong and where it causes them the most amount of headaches. So there's generally 3 steps I go through when I had to write assembly programs for that class. It was conceptualizing the problem, translating the problem from the concept into some form of logical series of steps, and then implementing that logical series of steps into the actual target language. In this case, it's MIPS assembly. So there's various problems that can arise in each of these categories. For conceptualization, it might be a fundamental lack of understanding of the problem. Hard to have someone fix your solution. Translation, if you have completely incorrect logical steps for your code, it's going to be hard to figure out what the assembly is actually trying to solve. And implementation, just have implementation problems. Why is signal bouncing? I love how it does that. Okay. If you have implementation problems, that's the easiest to solve because that's the most low-level problem. So you want your problems to be at the implementation layer instead of at the conceptual layer. Some of the problems with conceptualization come from just not actually reading the spec. I've had so many people where I ask them, okay, so you want me to help you, what are you trying to do? And they're like, I'm like, what do you want me to do? I can't read for you. Read the goddamn manual. And it tells you exactly what people want. It tells you exactly what people need. It tells you what to do in what order. Please do that, and it will solve a lot of problems. Take some time, go through it, read it, understand it. That's the most important part. You should have a thorough understanding of the fundamental problems that are being asked to be solved. Some more of those is that if you're trying to like take the idea and put it directly into assembly, I've tried that. It doesn't work well because assembly, as I said, is very verbose. It's very obtuse. It's going to having these abstract thoughts be put in a file. So one of the most important things that you can do is to actually write things out by hand. There's like just infinite studies on how this is better for memorization. And I know we're in the technology age and stuff, but like sometimes it's better to do things by hand on pencil and paper. It will help you with your understanding of the topic. It'll help you with figuring out what's going on. And it will help you spot bugs before they even pop up. It's kind of like doing the rubber ducky technique where you talk to your computer, you talk to a rubber duck, and just by having that manual stage of thought, you are having a better understanding of the problem and a solution to it. And I found that writing the steps out on paper by hand, just reading it and pretending like I fully understood it. And then there's problems with the translation of the code into some kind of pseudo language. One of the important things to do for this is you should be identifying common algorithms that you, or is, oh, I need a sorting algorithm on this part, or hey, it has me reading in a large number of numbers. That's probably going to be an array. That's a data structure. So you can identify these common puzzle pieces that you can start to like plug in and have reproducible ideas for. So you can say, oh, I need an array for this. This is what programming languages do. So kind of try and think about this in a data structure oriented way, and you can get the higher level ideas of what you're asking for. And then what this can allow you to do is it'll allow you to identify potential logic issues that might pop up, like, oh, what if they do this, or what if they enter -1 instead of a positive integer? And so it kind of allows you to break down the problem into more programmatic steps, really. And that's why you need to have some kind of layer between having the problem spec and having the code that solves it. And then you have problems with implementation. So this is just going to be you write something wrong in MIPS, you type the wrong register, you misunderstand how an operation works. These are the simplest to solve, and you want to reduce all your problems down to minor implementation details. So you need to figure out the register usage, memory management, how the data structures are going to be allocated and dealt with, idiomaticses, stuff that you can do that makes your life easier. And so once you boil these problems down through these 3 steps, it'll help you to get more idiomatic resulting code. All right, so with that, we can make a process to solve these problems that we've just laid out. Is everyone with me so far? Have I said anything that people aren't really understanding, especially anyone in concepts? I'm doing this to try and help out, so if people aren't understanding, please let me know. All right, awesome. So we have to do some transitions. So we have the assignment, which is our spec. We need to take that through conceptualization. We need to take that and translate it into some kind of programmatic representation, and then we need to actually implement that programmatic representation. So first off, we have the assignment to your concept of some sort. So you want to break this down into key parts. You don't care that the bear's name is Dory. You care that there is a object, bear, walking across a bridge or something. I don't know. But you need to break it into the fundamental details, and you need to really have a firm grasp of the assignment. If you don't understand the assignment, you're not going to write coherent code. Where our TFM comes in, please read the manual. The teacher writes it for you for a reason. They really want you to read it, and it will genuinely help you out in a lot of cases. I've seen a lot of circumstances where people fail to understand the document, where it actually, the questions they're asking me are actually detailed very thoroughly in the document that they obviously didn't read, and it just wastes your time and it wastes everyone's time, and it helps to do that. So then you need to take the concept and translate it into a representation. Typically, I just describe this as pseudocode. You can really have it be whatever you want, but typically you're going to be doing this in pseudocode of some kind. You're going to want to identify the algorithms and structures, as I talked about earlier. You're going to want to figure out how those fit into the spec and how those are going to fit into the final product. So this is going to kind of plug and play between the concept and the implementation. So you also want to figure out the structure here. That's why you're going to be doing it in pseudocode. You want to figure out what should be a function. What should I kind of modularize? What's dependent on what? Does the speed depend on being attached to another, like a ball or something, if you're doing a physics problem? And very importantly is the part where I talked about modularizing it. You want to have functions in your code. If you don't, you're going to have spaghetti code. And there is literally nothing worse in life than spaghetti assembly. That is one of the worst. If you thought spaghetti Python was bad, imagine spaghetti assembly. It's way worse. And no one will be able to help you with your problems because they won't be able to understand your code. So now you need to take it from the translation to the actual implementation. This is always going to step because you already have the defined logic set up. You just need to figure out the jump setups you need to do, the memory management. It's just formulas at that point, basically. And so you need to figure out, the biggest part is you need to figure out the idiosyncrasies that are going to pop up, the edge cases, the weird things that are going to happen between the programmatic layer and the implementation layer. So like most often it's going to be like your jumps. You figure out how to do the jumps properly. That can take a bit of mental arithmetic to work out, but you got to just work through it. And if you do it in a staged way, it will allow you to separate the potential issues there. So let's define like an actual process here. So I kind of just wrote this out as kind of like a reference, but this is what I did for my MIPS class, and this is what I did. And so for example, for kind of like a testimony on how this is not just crazy talk, I did this for my final project where you write like an entire freaking program out in assembly, like they give you nothing. And the first time I wrote it, it assembled and went through try perfectly, and I got an A on it. Like, this works. And I'm teaching you guys this because I want you to have the best chance of solving problems instead of just smacking your head on a table multiple times like in the previous figure. So first off, you're going to rewrite the project spec by hand. And it is important that all this is by hand. You want to get rid of everything that you don't need, get the project spec. If you cannot complete the project based on just the spec you write, you did not write it well enough, and you need to redo it. Identify the data structures and algorithms. That's simple. You've probably learned about whatever structures you're going to be working with, so it's probably going to be relatively fresh in your head. Then you're going to implement the spec in some kind of pseudocode language. I always used like a Python-like language because it's what I was comfortable with, but you can do really whatever you want. But then one thing that I found was really important is if you can translate, if you're taking concepts, you've taken mechanics, translate the pseudocode that you write into C. Because assembly has a very close relation to C, and so if you can write it into C, it's much easier to put it into assembly. And another kind of other thing you can do to that is, what I always did was I rewrote the C such that all the variables became MIPS registers. And so this kind of allowed me to more thoroughly define the steps I was going to take to translate it, so I wouldn't have to be substituting variables in my head all day long. It was just right there, and I could just walk through and implement each line of the C into assembly, which is the last step. And if you want to do a bonus round, you can actually write it out by hand on paper. I did that, and I would actually catch some bugs that I didn't catch the first time around. because when you're writing it by hand, it sticks in your memory better and you can kind of process the information better than when you're just abstractly typing things without thinking about them. So with that, does anyone have any questions on any of what I talked about? Like, want to challenge me, say that I'm an idiot or something? I don't know. Anything? Okay. So, with that, I have a shameless plug. If you like this, if you like assembly, you should check out the reverse engineering group. I started it. I really like doing assembly. I really like teaching people assembly, and reverse engineering is really cool. I like getting into places that want you, because not all software gives you the source code, and that's where reverse engineers come in, is when you have the source code and you want to find out what really gross things like that mean. That's going to be fun. You guys are going to have fun with that if you do the RITSEC CTF. So with that, does anyone have, oh, sorry, I forgot to say, the reverse engineering group meets Saturdays at 3 p.m. in Security Lab. That is 2410. We might change it around a bit due to some other things that are popping up, but for the best information in the RITSEC workplace, and join the reverse engineering group, and that's where all the information. What?
What?
I said Saturday, 3 p.m. Yeah. Anyways, join the workplace group, reverse engineering group. That's where all the information will be posted. Where if I change the times, that's where it's going to be. If there's cancellations, that's where I'm going to announce them. And with that shameless plug, does anyone have any questions at all about the material that I've talked about, or anything that they would like clarified? Yes?
How much of this applies to other types of programming?
Literally all of it.
Wow.
That, if the careful observer would note that earlier on, I said that you should implement it in the target language, not necessarily MIPS. This applies to a lot of things. Any other questions? Yeah.
I'm in Intro to Swen right now, and I'm recognizing some things that you're talking about.
Wow, it's almost like I took Intro to Swen too.
I'm sorry for your loss.
Yeah. It's a good class. I learned a lot about larger scale coding. Anyone else? No? All right.